Hello, everybody. My name is Chimei Liu. I'm working in Intel and focus on cloud storage. Today, I will discuss the persistent memory usage model in Ceph Crimson. First, I will introduce the persistent memory and then Ceph Crimson. The last one, I will introduce the persistent memory usage model in Ceph Crimson. So let's see the memory storage hierarchy first. From the bottom to the top, the hardware speed is from slow to fast. During the NAND SSD and the DRAM, there are two new devices. One is the persistent memory, and another is the Optane SSD. The persistent memory near memory performance has the rate almost close to the DRAM. And it is right in places, byte addressable, accessed by memory semantics. So you can use a load store to access it. And it is persist. It can be non-volatile and volatile. And it is memory-like endurance, multiple TB capacity, DDR4 attached. So the Optane persistent memory always used to improving the memory capacity. Optane SSD is used to improving SSD performance. The inter-Optane persistent memory has two usage models. The first one is the application direct model. In this usage model, the inter-persistent memory can be accessed by load and store or using persistent memory library. So it can be volatile or non-volatile. And in this case, another usage is that you can treat the persistent memory as a DRAM. It is treated as a separate region of memory from DRAM. Another usage model is memory mode. So in this mode, DRAM is a direct mapped cache for this persistent memory, and which is transparent to the application developers. It can be act as temporary storage for disk data. It is not persisted. So let's introduce the Ceph and Crimson. Ceph is an open source project, and it is object-scaled, scale-out distributed storage system. It is software-defined, hardware-agnostic, running on commodity hardware. The Ceph provided object and block and file interface in a unified storage cluster. Ceph must support replication enriching code, which provide the highly durable and available, and also provide enterprise features such as snapshots, cloning, and encryption. It can do the replicates and rebalance dynamically. It also self-managing, self-healing, and no single point of failure. It has also commercial support. Then where is Crimson in Ceph? So Crimson is the next generation of OSD. We just replaced the OSD in the classic Ceph by the Crimson. So the other part is not touched currently. In the classic OSD architecture, so there are several modules in the OSD. One is messenger, another is PG, OSD layer, and object store. So in each modules there is worker thread pool, and all these work threads share the resources, and it use the log to avoid confliction. And different thread will be switched on the different CPU cores. So there is a context switch when load the thread to the CPU cores. The I/O request coming from the messenger, and they use the work queue to do the DQ in queue to transfer the I/O request from the different modules. So classical OSD is resource shared, and there is the log and there is context switch. But in the Crimson OSD architecture, it is a run-to-complete module, and it shares nothing design. So on each CPU core, there is only one thread. The thread will not be switched out, so there's no context switch, and the resource is not shared, so we don't use the lock. The I/O request coming from the messenger and rescheduled by the seastar reactor. The reactors schedule the I/O request, the tasks, and from each module to the next module, it just use the function call to transfer the I/O request. So we avoid the context switch, avoid the lock, and run to complete without switch. In the I/O OSD Refactor, the async messenger is replaced by the Crimson messenger. Classical OSD PG service is replaced by the Crimson OSD PG service, and the BlueStar RocksDB is replaced by the SeaStore and B+3 metadata. All the OSD modules running on the seastar frameworks. So seastar frameworks provided a synchronized programming framework. Then let's discuss the persistent memory usage model in Crimson. In Crimson, we support multiple devices, such as the NAND SSD, Optane SSD, and PMEM. NAND SSD is high performance price ratio. So the Crimson target is to the NAND SSD, mainly supported NAND SSD. And it is heavily optimized for random read and sequence write patterns. So in the Crimson, we support the random read and sequence write according to the NAND SSD features. And Optane SSD, it is random block access for read and write. It's random write as fast as sequence write. When we rewrite to the extent, it needn't erase operations. So NAND SSD and Optane SSD, we use different uses model in Crimson. Also PMEM is byte addressable, and it is also can be persistent. So in the Crimson, we have the device manager layer, and currently we targeted to support the 3 different manager for each different kind of device. For the NAND SSD, we use the segment manager. We divided the NAND SSD into several segments and use the segment manager to manage the several segments, and use the segment cleaner to do the garbage collection. For the Optane SSD, we use the random block manager and the bitmap allocator to manage the Optane SSD. For the PMEM, we use the PMEM manager and the bitmap allocator to manage PMEM. So this is the architecture for the different device supported in the Crimson. And PMEM persistent memory usage model. Persistent memory can work as volatile memory or non-volatile memory. And as the volatile memory, it combined with the DRAM. So we can think the system memory is enlarged, and we can set a big cache size, catching more data and the metadata. The PMEM almost like a DRAM read latency. So read from the persistent memory can simply return a ready future without waiting at all. The write latency is slower than DRAM, but much faster than SSD. As non-volatile memory, the PMEM can add the metadata persistent storage. we can separate the metadata and the user data, write the metadata into the PMEM. The second usage is at the hot tier. So in the hot tier and cold tier support mechanism, and the PMEM can serve as the hot tier. Hot data will be stored in PMEM and the cold data stored in SSD. As volatile memory, and so in the SeaStore architecture, we have many metadata that is B+3 database, such as the ONode, OMAP, LBA, and the collection. So all the OMAP, all the metadata and the user data is cached in the allocate in the system memory. PMEM as extended system memory serves as volatile cache, which is transparent to application. So provide a big cache for metadata, reducing read latency from SSD. So at this situation, the PMEM, just like the system memory, you can use it like DRAM. As metadata persistent storage, in Crimson, the ONode, OMAP, LBA tree is the B+3. When we modify the node content, we will use the copy on write currently and record the data, write the data information into the SSD segment. So when we support the PMEM, PMEM is byte addressable, non-volatile data updated in time. We can use the PMEM as KV, that the tree node metadata storage. So since it is non-volatile and data updated in time, we needn't do the copy on write, needn't record the data of tree node. And even it depends on the performance requirement, we can load the tree node into the cache or not. We can just read from the node content from the PMEM or write to the PMEM. If it is depending on the performance requirement. Since it's read is close to the DRAM, but write is slower than DRAM. So we can load it into the cache or not. As another situation is as faster journal. So journal is the recorded data storage. Provide faster journal write and reduce write amplification. Since it is byte addressable, we needn't to do the block aligned. Currently, we write to the SSD segment. We have to align the data to a block size, so that will introduce the amplification, write amplification. But for write to the PMEM, we needn't do the block aligned. It is byte addressable. Rewrite without erase operation. Yes, it also reduced the write amplification. And the separate data recorder with fresh block and make recorder trim quickly. The third situation is that we can use the PMEM as the hot tier. PMEM serves as hot tier, and SSD, non-SSD, serve as cold tier since PMEM is more expensive than the non-SSD, and but it's faster than non-SSD. And PMEM is big enough and fast enough to reduce the cost associated with moving objects into or out of the hot tier. PMEM is also persistent, so no need to write data to the journal stream, reduce the transformation submission. Only need to fix LBA remapping transparently to point to the new PMEM address. So when the client sends the request to the Crimson and SeaStore, the data can write to the hot tier, that is PMEM first. And when the PMEM is reaching some capacity and move the object from the PMEM to the non-SSD. So PMEM benefits. PMEM, when we use PMEM in Crimson, it can accelerate the transaction submission. The journal efforts is reduced because PMEM blocks are persistent prior to writing to the journal. So all we need to do is link the new blocks in PMEM physical address without the need to record any data or rewrite for the overwritten blocks to the SSD. It can accelerate the garbage collections. The journal size is reduced, and the PMEM blocks do not need to be rewritten again from dirty to clean when trimming the journal. It can accelerate extent loading. PMEM block is directly readable without the need to copy to DRAM. So read speed is close to DRAM. So that is the PMEM bring the benefits to the Crimson. So that's all for today's discussion. Thank you.